Okay. All right, so it says, in a previous adventure, we learned to use substitution when possible. We also learned that substitution does not work at a hole in the graph. So there are 3 techniques that can be used to find limits as we approach holes. 0 over 0 is called an indeterminate form because as we approach 0 in the numerator and 0 in the denominator, different things can happen. And we're going to look at other indeterminate forms like infinity or infinity in the denominator. So for now, we're not really talking about those situations. So the strategy that you kind of already watched a video about was factoring. So it says a hole is referred to as removable discontinuity. So it's something that can be removed from the function. This term indicates that we can use algebra to find the y value of the hole. Be aware that in many calculus problems, the c value that x approaches may give us a hint for factoring. So guess what? I'm approaching down here a value of 3. And look, it's approaching 3 as your asymptote or your hole, right? So what it's saying is whatever the limit is, that might be your hint of what you're trying to cancel out over here. So how would I factor? When I plug in 3, I get 0 in the denominator. So I can't use substitution to find the y value. So this is a rational function. We've already done this before. How would I factor the numerator so that I could cancel some things out? So what does the numerator factor into? X minus 3 times x minus 1, and I have x minus 3 in the denominator. So those x minus 3's cancel out. We've already done this year in rational functions. So what I want to do is I want to plug 3 into what I have left. So what would the limit or the y value be for this function? When you plug in 3, you get 2. So the limit is 2. And if I looked at the graph of this function, so let's see, it's y equals x squared minus 4x plus 3 over x minus 3. I like this as kind of, this is like your bridge to calculus because it puts together things that we've already learned this year, like factoring and rational functions. It looks like a straight line, right? It's the line y equals x minus 1. So it has a y-intercept at -1 and a slope of up 1 over 1. When I go to 3 in the table, see how there's an error in the table? It might be hard for you to read this, but what is it approaching from the left side? It goes 1.98, 1.99. That's approaching a value of 2. And then this is 2.01, 2.02. So it's approaching a value of 2, but 3, 2 does not exist because it was a hole. So using a table is a strategy to find a limit. Using factoring and canceling is a strategy to find a limit. A limit is just the y value. I wrote down that these formulas may be helpful. We kind of looked at these briefly in our polynomial unit, how to factor cubic functions. I would always give you these as formulas on a test or quiz. You don't have to memorize them, but if you see something like x cubed plus 8, you have to be able to use the formula to factor it if you're going to use factoring for this example. So see how when I plug in -2, I get 0 in the denominator? So I have to try factoring and canceling. So the numerator is just difference of squares, x plus 2 times x minus 2. And then the denominator, if it's x cubed plus 8, I go up here to the formula, right? A cubed plus b cubed. I just want a plus b. So I'm taking the cube root of both terms of that. So I would just get x plus 2. So there's my x plus 2 that I'm going to cancel. So now I have a trinomial. So the trinomial in the function says take a squared. So in this case, it'll be x squared. And then the formula says write minus a times b. A times b is 2x, so minus 2x. And then the formula says write plus b squared, so plus 8, because 4. 2 squared is 4, so plus 4. So I factored the numerator and factored the denominator so I could cancel my x plus 2's. Now I can plug -2 into this function to solve for the y value of the whole, which is the limit. So what do I get? -2 minus 2 up top. And then I'd get +4, +4, +4. So what's that? -4/12? Is that -1/3? And if I was going to do the same thing and check it on my calculator, because that's a strategy, x cubed plus 8. When I go to my table at, when am I approaching? -2. So I get -0.3325, -0.3342. So -0.3333 is right in there where it says error. So using a table of values would get that same answer. All right, here is still a factoring strategy, but it says sometimes you may need to do some simplifying before factoring is possible. So again, if you try substitution, you plug 0 in, you get 0 in the denominator. I can't factor this until I actually FOIL this out and do some simplification. So it just falls under a factoring strategy, right? This one was just ready to factor. This was factoring using cubic. This one's factoring after we do simplifying. So if I FOIL out this binomial, I'd have x squared minus 6x plus 9 minus 9 over x. Well, 9 minus 9 is 0. So I really have x squared minus 6x over x, which now is going to factor. So how can I factor the numerator now that I've FOILed everything out? What strategy can I use to factor the numerator? It starts with a G. GCF. So the GCF is x. I would have x minus 6 left in the numerator, and I have x in the denominator. So now see how that factor cancels? Remember they said whatever that x is approaching value, that's probably a hint for what you need to cancel out. So now that I've canceled out x, I can evaluate x minus 6 by plugging in 0. So what is the limit of this function as x approaches 0? -6. Can you do number 4 the same way? It's an h instead of an x because when you start talking about derivatives in calculus, you'll actually see this function again. But this is just what is the limit when h approaches 0. So if you could FOIL out the numerator and factor it the way we just did number 4, so you get that 49 14h h squared, but the minus 49 adds up to 0 with the positive 49. When you factor out the h, you get 14 plus h left in the numerator. So when you plug in 0, you get 14. And you're going to see this formula when you get to calculus. So even just having seen it once before, it'll help it be cemented in your head when you get to calculus. It'll make more sense once you get to calculus. So that whole front page is just the strategy of factoring. If you can't plug it in because you get 0 in the denominator, try factoring first because you're not going to have a calculator on a lot of the evaluate. You could always use your calculator, right? But so factoring, these are all factoring strategies. So there's 2 strategies on the back that we're going to have to revisit again on Friday after your test on series, but at least if you've seen them once, your brain will start to recognize that this is a method. So this is something called just rationalizing and using the conjugate. It's a strategy that you would never think of on your own. So I'm teaching you this strategy. When you see a radical in a problem and you can't plug in the number because you get 0 in the denominator, try this strategy because this is one of the ways that a problem could be solved. So it says, recall that the conjugate of a binomial with a radical can be used to eliminate the radicals, like a plus b, a minus b. A similar method could be used to evaluate limits when there's radical expressions. So this time I have a radical expression in the numerator. So we actually want to get rid of the radical expression that's in the problem altogether in the numerator, and I'll show you why. So if I want the conjugate of what's in the numerator, I'm going to rewrite it as the square root of x plus 1 plus 2. So I keep the terms the same. So square root of x plus 1 stays the same. The 2 stays the same. But instead of a minus, I'm going to put a plus. And I'm going to multiply by the same thing on the top and the bottom, because that's like multiplying by 1. So I'm not changing the value of the problem. And we're going to FOIL out the numerator to see the magic. So a square root of something times a square root of something, if they're the same, just gives you the something. So the square root of x plus 1 times the square root of x plus 1 just gives you x plus 1. Your outer plus your inner are opposites, right? So they add up to 0. That's the whole point of using a conjugate, like difference of squares. So the other term is last. Negative 2 times positive 2 is negative 4. So what does that give you in the numerator? It gives you x minus 3, which is a beautiful thing because the denominator's problem was x minus 3. You do not want to do FOIL in the denominator. So you want to leave this as the factor square root of x plus 1 plus 2. So I have this kind of yucky radical in the denominator, but at least my x minus 3's can cancel out. So that gives me 1 in the numerator, because anything divided by itself is 1. And I've got this kind of yucky thing in the denominator, but I'm just going to plug in what I want to find for x. I want x to be 3. Right? So once I've factored and canceled, you're going to plug in your x value and see that now you can find the limit. You can find the y value. So this is kind of like a hole. It's like a tricky way to get rid of a hole. So you get 1 over 2 plus 2, so 1/4, right? Because this is the square root of 4, so that's just 2. So I was able to evaluate it using conjugates. Could you try number 6 the same way? So you're going to set up number 6 using the conjugate of the numerator. So your conjugate would be the square root of x plus 8 plus 2 this time. Square root of x plus 8 plus 2. So the only thing that is changing is this negative sign in the numerator became this positive sign. That's a conjugate. So see if you can use that same strategy to solve for x. Negative 4, you get the radical of 4 right here. So 1 over 2 plus 2 again. That's a coincidence that they came out to the same, but you know, so this is like someone made this problem up so that it would work. It might not always work with conjugates, but the chances are, I mean, this is just kind of a surface view of limits that we're going into. So chances are if there's a radical, I'm going to make up the problem so it does work for you. Okay, and then the last strategy that we're going to end on today is just this idea of a common trig form. So they are functions that involve trig functions. So there's just some general rules. It says there's some limits involving trig functions that you should recognize in the future. Here are the most common ones. So all of these fail when you plug in 0 because you get 0 in the denominator. So whenever you plug in 0, if you have the sine of x over x, it will always equal 1. So this is just something that, you know, someone has figured out looking at trig functions that this always is true. This is the one that you kind of need to know and memorize for our purposes. Whenever x is approaching 0, and it's the sine of ax over bx. Remember from trig, a changes the period of the graph, and right, b would kind of change the stretch or shrink of the graph, I guess. You can strip the coefficients and it'll always equal a over b. So this is only when x is 0, and it's only when you have the sign of a number divided by another number with x. That's why this one works out to 1, because this is 1x over 1x is 1. So ax over bx. These are kind of nice to knows. Maybe you'll need to see them in calculus. If I asked you these, I would give you these formulas. So you don't have to memorize these. You'd either have substitution that would work or your calculator. But if you ever are plugging in 0 here, if you had 1 minus the cosine of x over x, it'll approach 0. If you had x over the cosine of x, it'll approach 0. Those are trig identities. They're all derived from this circled one. So if you ever saw I'm approaching 0 and it was the sign of 8x over x, if you just strip those coefficients, the graph will approach 8 because 8 divided by 1 is 8. And the same thing with example 8. So sine of x over x, you're allowed to strip those coefficients and it will approach 2/3. So to me, this is not as important because we're just kind of memorizing it for now. But if you see sine of x over x, start thinking about, oh, there's something like special going on here that I should remember. Not that you'll remember it by calculus, but that's the only trig form that I'm going to have you memorize for our unit is this one. So that is all for today. We're going to do this guided practice next time to kind of like relearn this.